In 2.1, we sort of introduced the idea of separable solutions, and we took our big psi, which is our normal wave function, big psi of x comma t, and we split it into a time-dependent solution and a time-independent solution. So we have little psi of x, which is purely x-dependent, and multiplied by phi of t, which is purely time-dependent. And apparently, we are able to decompose wave functions into this form. And in cases that we are allowed to do this, we have some very interesting mathematical results that are very useful, as we've proved earlier on in 2.1. We've also solved for the time-dependent function psi of t, which takes on the form of ce to the negative I over h bar times et, where c is some arbitrary constant that eventually gets absorbed into our normalization. And then E is our separation constant, which also turns out to be energy, and then T is time. So now we can actually begin solving for the time-independent portion of this separable solution. And as we've said earlier on, the method for solving for little psi of x, and also the form that little psi of x takes on, will vary quite widely depending on the specifics of our system. To be more exact about that, the actual method for solving for little psi of x will heavily depend on the specific form that our potential takes, because our exterior system will always be defined by the exterior potential. So we can start off with the infinite square well, which is in many ways the simplest system that you can have that isn't trivial. So our infinite square well is going to be defined in the following way. We have some potential v of x, and it's going to be equal to 0 inside of our range, so from 0 to a in this case, and it's going to equal infinity everywhere else. So let's visualize what this actually looks like. If I have, let's do this in black actually. If I have an x and a y axis like this, and let's say that this is x and this is v, then my potential function is going to look like this. So let's say that this is at A. So what happens here is that my potential is 0 inside of this range from 0 to A, and it's infinity everywhere else. And this looks like exactly what this actually represents physically. We call this potential an infinite well because it literally is physically, in all senses, including physical, it is an infinite well. Imagine like a ball stuck at the bottom of a very big hole. And at the top of this hole, the potential is equal to mgh if we use mechanical height energy. And if we say that, this hole is infinitely deep, then the height is going to be infinite at the top of this well. Therefore, the potential will equal infinity outside of our well and equals 0 on the inside of our well. This is the exact same scenario that we're describing here. So because of that, we can literally think of this physically as just having some sort of ball in like this infinitely deep hole. Now, obviously, this is not a physically realizable potential, because in real life it isn't possible for some hole to have an infinite depth. It's not possible for us to contain an object in something that has like infinite durability, or some cage with walls of infinite height. It's not possible. However, this is a very nice situation, because this potential is a very simple potential, and it actually ends up being very simple to solve as a result of that. And by first looking at this and solving this, we can get some background and something to build off on as we move on to more realistic and also more complicated systems with more complicated potentials. So let's start by solving this physically impossible but very idealized system, where we have an infinite well with the walls that go up to infinity and a ball that's stuck in the middle and can never go out. So first off, let's recognize something. We want to find psi of x in two regions, inside and outside of the well. Because we have two different scenarios here. We have the inside of the well, where v is a constant, being 0, and the outside of the well, where v is another constant, being infinity. So obviously we want to sort of solve these two scenarios. Well, first off, let's start by looking at the infinity case, because we can actually link this back to sort of classical mechanics. Because if we hypothetically go back to our imagination scenario of having this physical ball inside of this infinitely deep well, well, classically, there is no possible way for this ball to be anywhere outside of the well. This well has walls of infinite height and infinite thickness. We can never move this ball out of the well. For all intents and purposes, the entire universe is effectively contained inside this well. So because of that, we can say that 100% of the time, this ball will always be inside of this well, which is constrained from 0 to a, let's say in one dimension. In quantum, because of the specific fact that our potential v is actually at infinity right now, sort of this is analogous. If we have a particle, it is trapped effectively in between 0 and a, because the walls of this potential well are effectively infinity, and the particle will never be able to sort of break through. This is not necessarily true normally. And this is actually one of the big sort of differences between quantum mechanics and classical mechanics, is that in classical mechanics, if you have a ball inside of a box, it can never leave the box, assuming that it's not hitting the walls of the box hard enough to sort of break it. But in contrast, in quantum mechanics, if we have a particle inside of a box, there actually is a probability for our particle to break through the box. However, we will not have to worry about that in this specific case because of the fact that the walls of our well are at infinity, not some finite number. We will analyze the case where v is finite later on. However, right now, currently, for all intents and purposes, this is an indestructible infinite wall, and our particle will never be able to go through it in the exact same way that a classical ball would never be able to go through the walls of a well that is infinitely thick and infinitely tall. So because of that, we can confidently say that outside of our well, psi of x equals 0. There is a zero probability, or there's a zero possibility / probability of ever finding our particle not inside this well, because of the fact that our potential is currently at infinity. Once again, once we start analyzing cases where v is not infinity, where it is some finite number, this will change. However, we don't have to worry about that right now. Right now, we're looking at a infinite well, therefore we only have to focus on that, and as a result, we will never find our particle sort of anywhere outside of our well. It's not possible to find our particle here or here. It can only be sort of within this tiny range from 0 to a. So now let's now that we've obtained sort of this trivial result for outside the well, let's look at inside the well. So inside the well, obviously we have to resort back to the Schrodinger equation. We earlier on in 2.1, we've defined the Schrodinger equation for the time independent function to be the following: negative h bar squared over 2m multiplied by the second derivative of psi with respect to x squared plus our potential v times psi again is equal to our separation constant, or the energy E times psi again. So our goal now is to solve this expression for when we're inside of the well. And instantly, we should realize that we can cancel out v, because v is 0 inside the well. So now we just have negative h bar squared over 2m times the second derivative of psi with respect to x squared. And this is equal to the energy, or the separation constant E, times psi. Hopefully, at this point, you sort of already see where this solution is going. But if you don't, that's also okay. Let's just keep going and simplify this a little bit more. So if I move everything here onto the other side, what I'm going to get is I'm going to get that d2 psi with respect to x squared is going to be equal to negative 2me all over h bar squared times a little psi again. And hopefully you see here that m is a constant because it's just a mass. E is our energy, which we defined earlier in 2.1 to be constant necessarily. H bar is also a constant. So there is nothing stopping me from sort of rewriting this as negative k squared times psi, where I'm defining my k to equal the square root of 2me all divided by h bar. And the reason why I'm going out of my way to do this is because if you look at this now, this is pretty much the form for a simple harmonic oscillator problem. And we've done this many of times before in classical physics. When we have a second differential equation, or when we have a second order differential equation of this form, this is the exact form for simple harmonic oscillators, and we already know sort of that this resolves into the following form of psi of x equals some constant a times sine of kx plus b, which is another constant, times cosine of kx. And so we have effectively solved for our time independent solution for the simple potential well, or for the infinite potential well, I'm sorry. And at this point, all we have to do now is sort of find out what these constants a and b actually are, because otherwise everything else has sort of already been defined for us. Now, originally in classical mechanics, when we're dealing with problems exactly like this, in the form of a harmonic oscillator, our goal is to find the constants a and b. And for harmonic oscillators, this is normally done by sort of looking at the initial conditions. In quantum mechanics, we do the exact same thing, except instead of the initial conditions, we look at something called the boundary conditions. And to understand what that actually is, we need to recognize that there are a few conditions that little psi kind of needs to meet in order to sort of be valid. So little psi of x has two conditions that must be met in order to be valid. So let's look at these each one by one. So the first condition is that psi of x must be continuous. And the reason why that psi of x must be continuous is because, once again, we sort of require the fact that the magnitude or the integral over all the space, so from negative infinity to positive infinity, of mag psi of x squared dx must equal 1. We sort of required this as a normalization, under normalization, and if psi was not continuous, this would no longer be true. If we had some function which sort of just randomly decided to break off, let's say like this, this is no longer sort of, this will not integrate to sort of 1. This will never integrate to 1 because we would never be able to get a valid integral for something like this. We would just get equations that break down. The second condition, let's go back to the alphabet, is that the derivative of psi of x must also be continuous. Now, this second expression, or the second statement, we can't exactly prove currently. We will prove it later, but for now, we will sort of do the thing that we've always done so far, which is to sort of take Griffiths' word that this is true. So now, let's sort of apply these two rules onto our wave function, which is a sine kx plus b cosine kx, and try to find a and b. Looking at the very first condition, which is that psi of x must be continuous, Well, we sort of have a definition for that because we already know from earlier on that outside of our well, psi of x equals 0. So if psi of x must be continuous over all of space, then we can sort of imply condition 1 to represent that psi of 0 must equal psi of a, which must equal 0. Because if we look at our well, v of x just instantaneously jumps to infinity at 0 and a. So if psi has to be continuous, and we also recognize that psi must be 0 when v equals infinity, we necessarily require psi to equal 0 at these 2 points, at 0 and a respectively, because otherwise we would have some sort of discontinuity as we go from 0 to whatever infinitesimal amount that is less than 0, or from a to whatever infinitesimal amount that is less than a, or greater than a in this case. Now, if we use this condition, well, we know that psi of 0, we just plug in 0, then we have a times sine of 0 plus b times cosine of 0. Sine of 0 is just 0, cosine of 0 is just 1, so this equals b. So, therefore, from this point, we necessarily require that sort of b has to equal 0, because this has to equal 0, psi of 0 has to equal 0, so therefore b must equal 0. So, if we take our wave function that we've defined so far, we now know that sort of b must equal 0 and cannot be in this expression, so we just erase this. Erase the plus sign and also the mark I accidentally brought down. So now we know that psi of x is purely a sine function, no cosines. Next, we have sort of a few more possibilities. So let's analyze sort of psi of a. So we know that, so condition 2, we know that psi of a must equal 0. So this equals a times sine of k times a. And from this point, we have two possibilities. The first possibility is that if we want this to equal 0, then a has to necessarily equal 0. However, if we enforce that a equals 0, then we just get a trivial solution where psi equals 0, and that we don't really care about that. That doesn't have any interesting properties. So therefore, we will not assume that a equals 0, and we will instead take the second definition, or the second possibility, which is that sine of ka equals 0. And if sine of ka equals 0, well, that necessarily tells us that since sine is a periodic function, ka must equal either 0, plus minus pi, plus minus 2 pi, and so on and so on and so on. From this point, we can recognize that if we say that ka equals 0, then we sort of get the exact same sort of trivialness that we get from earlier on. So we can sort of ignore the ka equals 0 case and look at all the other solutions. So if we only look at these solutions, then what we get is that ka is equal to plus minus n pi. Now, finally, the other thing that we have to recognize is that the negative solutions also aren't sort of particularly interesting, because we sort of, for sine, we know that sine of negative x just equals negative sine of x. And since we have sort of this arbitrary constant that's in front, this negative can just automatically get absorbed into our constant. So because of that, these aren't necessarily that interesting either. So what we actually want to focus on is that ka equals positive n pi. So if we isolate k, then what we get is that k is apparently equal to n pi over a, where n is equal to just some positive integer, 1, 2, 3, whoops, 1, 2, 3, etc., etc., etc. And from this point, we have a few interesting properties that we can sort of look at. Because in classical physics, when we're dealing with the simple harmonic oscillator, we sort of determined the constants A and B that we've done so far by looking at the initial conditions of the problem. In a quantum well, which is what we're doing right now, we did not determine A and B. Rather, we determined K, which is inside of our cosine terms. So normally K is something that's given to us for a harmonic oscillator. We know what it is because it's just generally the spring constant, which is a constant we know. In this case, we don't actually know what K is. K is some sort of constant that is dependent on sort of the mass of our particle, the energy of our particle, the reduced Planck constant, etc., etc. We don't actually know what that is. And we ended up sort of finding out what K is by looking at the boundary conditions of the problem instead of the initial conditions of the problem. This doesn't have any important implications. We're just sort of looking at it because it's an interesting dichotomy, or to compare sort of the differences between a quantum well and a simple harmonic oscillator, because these two things are very similar, but sort of have these really weird differences that we don't really know the significance of right now. Maybe later they will come into play, but for now I just want to sort of shout this out as a sort of a point of interest. But let's sort of go back to what we're doing in the first place, which is looking at K. So we've defined K, and note that earlier up here we also defined K as well. So we can define this in terms of each other. So apparently, well, 2me over h bar, which is what K is apparently equivalent to K, which is equivalent to n pi over A. So at this point, we can solve for the energy E in this case, and what we'll get is that E is apparently equivalent to, let's see, h bar, this is going to be equal to n squared times pi squared times h bar squared over 2ma squared. Yeah. And earlier on in 2.1, one of the things that we sort of said was that the separation constant E was the energy, and that apparently it takes on definite values. And I sort of threw that at you without proving it, because that's sort of what Griffiths decided to do. And now here in 2.2, when we're looking at our very first example of a system with some potential V, in this specific case an infinite square well, we are seeing mathematical proof right here that the energy is apparently dictated by n, which is a integer, and because of that, E apparently takes on multiple definite values, or sort of this range of values. And this result should be shocking, or it should not. You should not be accepting this sort of as if it was obvious, because unlike sort of in classical mechanics, where energy takes on this full continuous spectrum of possible values, systems in quantum mechanics apparently have certain energies that E can take on and no other energy values that they can take on. E is not a spectrum, but rather a discrete set of numbers. So evidently, just saying what we've been saying so far, which is that everything in quantum mechanics is indeterminate, is not entirely correct. Apparently, certain things, such as position and momentum, are indeterminate, but other things, like energy, are not indeterminate. Rather, they are determinate. So this is sort of a very weird sort of result, and we will gain more insight onto this later on. But for now, just recognize that sort of what we've learned so far about quantum mechanics and indeterminacy is not necessarily the entire picture. Evidently, there are certain values like energy that are determinate in quantum mechanics. We don't know why they are determinate so far. Later on, once we introduce sort of Dirac notation, it will become sort of easier to prove it. But for now, we simply have to accept that apparently in quantum mechanics, not everything is indeterminate like we initially thought. we are almost done with sort of our long derivation journey here. The only thing that we have to do left is, or the only thing we have left to do now is to actually find what the normalization constant A is. So let's just do that right away. So we know that psi has to be normalized, so we can enforce the condition that the integral from, and here, instead of from negative infinity to positive infinity, we're just going to do from 0 to a, because that's the only area where our wave function is defined anyway. And we're going to take the magnitude squared of everything, so the magnitude of a squared, and then sine kx is a real term, so we just square it normally without including the magnitude signs, because that makes it trivial. Sine squared ka dx, and we necessarily require that this equals 1. From here, this is just something that we can just plug into an integral calculator. We could do it on our own, but once again, physics course, not math course, so I'm just going to shove this into an integral calculator, and what I'm going to get is that the magnitude of a squared, and then this integral of sine squared of ka is going to evaluate to a half, and this necessarily equals 1 under normalization. So finally, we move a to one side, so we get a must equal the square root of 2 over a. And from here, it's just a matter of plugging this in. Our spatial wave function for the Schrodinger equation in terms of separable solutions for the infinite square well is going to be equal to the square root of 2 over a times sine of, and we're going to replace k with what it equals here, n pi over a, times x. And here a is sort of like the width of our quantum well. And as a result of that, we have, for all intents and purposes, finished solving this system.